Hi everybody, welcome to Climate Change Calculated, this time a Corona update number 3. My name is Gerald Schuller. Today I want to talk about how we can compute the underdetection rate of Corona cases, and I want to show an online Corona program or programs for computing the underdetection rate and also with a 30-day prediction. If you're interested, stay tuned. So, what we know in the meantime about the coronavirus is that it spreads through aerosols that can stay in the air for hours. So that's the dangerous part, especially staying indoors. And keeping your distance and wearing masks reduces the concentration of the viruses and thus reduce the likelihood of an infection. So basically having a mask first distributes the viruses when you breathe out, and it also reduces the concentration when you breathe in. So that's the good news. The bad news is that the virus attacks the blood vessels, which hinders or blocks the blood flow, which can also cause permanent damage. When you have blocking the blood flow of certain organs, then that's bad, right? So that's a considerable risk of this virus. Also interesting news is that the average age of those infected has dropped significantly from 52 to 36 years in Germany, and that's partly good news. So when you look at this German newspaper here, we can see the age distribution, how it changes over time. So it says infected become younger. So when you scroll down, you can see the plot. And here you can see the calendar week on the horizontal axis. And here you can see the average age of infected. And you can see here it's going up in spring, and then here it goes down during the summertime. So here the average age is now much lower, and that's probably because younger people tend to meet more people in parties and don't wear masks and travel more often and bring the virus home. But it's only a matter of time until this goes up again, because the average age of Germany is about 42. And if everybody is equally affected, then we should become at this average age of 42. Right. Yeah, so this is what I just mentioned. The good news is younger people have a low mortality risk from corona, from the new coronavirus, from dying of COVID-19. And this reduces the overall infection mortality risk. And you can see this infection mortality risk here in this Nature article. So when we open it, we can see the distribution. So it's most deadly in the elderly. And when we scroll down, we can see these tables. And here you can see the city of Geneva. Here's the country of England, and here's the country of Spain. So we can see Geneva is the city, so the numbers are not really comparable to entire countries. And you can see here above 75 in England or above 80 in Spain, we get a infection-based mortality risk of about 11 or 7%, which means from all infected, 11% will die. And this goes down significantly when you go to the younger population. So in the middle age, 45 to 64, or here 50 to say 69, we have it about 1%, right? Here's 1%, here's about 0.5%. So when you average out everything, you usually get about 1 to 2% overall age groups. But here you can see it depends significantly on the age. And that's why we also see changes in the infection rate, mortality, infection-based mortality rate when we have a lower age average for the infections. But then that will probably change when the virus again reaches the older population. Yeah, the problem with tests is that we can only detect a certain fraction of all infected, right? Tests have false positives and also false negatives. The tested are usually only persons returning from at-risk countries, like when they come from vacations in Spain, for instance, or with clear symptoms, so when they are already sick. So those are usually the ones that are tested. And that means of those tested positive, we have a higher likelihood that they fall sick. So the percentage of positive tests in Germany in September was around 1%, right? So it's actually not that high. So here you can see it. And you can also see that it slowly is increasing. So here you can see the calendar week. And you can see the positive tests. And you can see how the percentage of the positive tested goes up, right? So that means the virus is spreading. So the numbers are still relatively low, but they are about to rise. So when you look at the test accuracies, we can find how good they are with the false positives and false negatives. So here you can see a table of those test accuracies, and you can scroll down and you can see different tests from different companies, and you can see the sensitivity and here the specificity, and this is connected to the false positives and the false negatives. What's interesting is in this table is also that you get here different rows for the same test. And this is because they use two different gene targets. So these are like taking two tests at once, targeting two different genes. And this is important for the false positive, which we will see in a moment. So for a single test, we have false positives, which are computed by computing 1 minus specificity, which is approximately 2% for those tests. And this results to a factor of 0.02. So 2% is a factor of 0.02. And this is in the same order of magnitude as the percentage of positive tests that as we just saw here. Right. So that's not so good. But it has the easy solution. And that is we simply take two independent tests. Right, either one after the other after some time, or in the case we just saw with two genes. Right, if we assume each gene is one independent marker, then we have two tests at once. And these are called dual target tests. So two gene regions are tested, which is like two tests in parallel. Right, so you can see a little bit more about it. And you can see how the testing is done. And you can also see the two target tests when you go down here. Scroll down. Yeah, PCR is the usual. And here, if you have a negative, you still have the possibility that you are infected. That's also why you need a second test in that case. Yeah, so there's a lot to read about the details of the tests. And yeah, right. So with two independent tests, the probability that the first test is positive and the second test is false positive is the product of the probability that each single test has a false positive. So this is called a compound probability, right? So when you have, say, you throw a dice and you have a 6 in the first time and you have a 6 in the second throw of the dice, then the probability that you have 2 6s is the product of the probabilities of an individual 6. So here you can read more about it in this link. So here, compound probability. So here, this is the probability of event A and event B, and if both are independent, then this is the product of the probabilities of the individual events. And this is what we assume here. We have 2 independent events. Each has a low probability, and when we calculate the product, we get a very small number, which corresponds to 0.04%. Right, so this is a very low probability, much lower than the percentage of positive tests, and that means we get a very accurate detection here. Right, so this is a very simple solution. There are also false negatives, which are computed as 1 minus the sensitivity, which comes out to about 4%. So even in 4 tests where you have a corona infection, 4% of those say there's no infection. So that's why if there's a suspicion that there's an infection, the test is also repeated. And this is also described here in this test strategy by the Robert Koch Institute. Right, so this is what it says. If there's a suspicion, in a second test is done. Yeah, but more important than the false positive and the false negative are those infected who are not been tested or that have not been tested at all, right? Those people who are falling through our search grid, basically. So the question is, how can we actually estimate the true number of corona infections? So the answer is using the under-detection rate. Right, so basically this estimates how much of the infected we actually detect with tests. So how can we actually compute it? We know that all who are tested positive for the coronavirus, the detected, either recover, they are called recovered even if there's permanent health damage, or they die, right? So first they are tested positive and then they have either of those 2 outcomes. Hence, the sum of the dead and recovered equals the number of detected before, right? And this leads to the case fatality rate. So the case fatality rate is defined by the number of dead divided by the number of tested before, which is the number of dead plus the number of recovered, right? And this is also defined here in this Wikipedia page. There you can see the definition of case fatality rate and also the infection fatality rate, which comes next. So the infection fatality rate is defined as the number of dead divided by the number of infected, right? And note that the number of infected now is larger than the number of detected. And this comes from our under-detection rate. So now we have the connection. So this infection fatality rate is difficult to estimate because it depends on the people that are infected, which we didn't detect, right? And that's why it's estimated in controlled environment like a cruise ship or in small towns where everybody can be tested. And if we have this number, then we can obtain the under-detection rate as case fatality rate divided by infection fatality rate. So this basically is the same as the number of infected divided by the number of positive tested. So observe that here basically when we divide those two, the number of dead should cancel out because the number of dead should be identical in both cases because we assume that the ones who are not detected have a mild disease and don't die from it. right? If they are dying and are not counted, then this doesn't work. So for this under-detection rate to be precise, we need to have a precise count of the dead here, of those who died from the disease. And this is a problem in countries like, for instance, India, where in the countryside you have basically not much infrastructure, and if people there die, then basically they don't enter in any statistic. And that makes the estimation then difficult. Yeah, so hence the under-detection rate is the ratio of the case fatality rate to the infection fatality rate. And the estimation of the infection-based fatality rate varies. So actually I showed a few estimations in my Corona update video, and it usually ranges between 0.6% and 5%, roughly. And we saw a similar range in the website that we just saw from England and Spain. So it should be in this range for the population. And I assume it to be 2%, just to have a value for the computation. And here you can also see that we have an inaccuracy factor of about 2. So it can be a factor 2 higher, it can be also roughly a factor of 2 lower. Right. So I don't expect the estimation of this under-detection rate to be better than this factor of times 2 or divided by 2. Yeah, and I already did a calculation of the under-detection rate in my Corona special video in mid-March, and also one in the Corona update in mid-April. And I got actually very similar values. In mid-March I got an under-detection rate of 3.5, which means the true number of infected is 3.5 times higher than the detected one. And in mid-April it got somewhat better, probably because the detection, the tests were better, which means more widespread. And I obtained an under-detection rate of 2.3. Right. And interestingly, recently there were some studies done who actually measure this under-detection rate. Here you can see the study. And here you have 2 places, 2 towns where they did this study, where they basically tested everybody in those towns, Kupferzell and Bad Feilenbach. And they found in Kupferzell that they call it Dunkelziffer, which is this under-detection rate of 3.9. And in Bad Feilenbach they found 2.6. So this is actually very close to my numbers, and that shows that this assumption of those 2% for the infection-based fatality rate is actually a good estimate or a good assumption. Yeah, so fits quite well, and that shows that this assumption works for my calculation. It's about right. This 2% is probably going down in Germany because of this reduced average age of infected recently. But then I assume it also will go up again. So the actual observed corona progression since March is essentially as in my optimistic scenario from March. So that's good. There are also noticeable deviations, actually downwards, which is good, due to staying at home from about mid-March, and then the introduction of the mask and distance requirement, which seem highly effective. So this is actually shown from my models. There's a dip downwards at around end of March as the result of those measures. So that actually shows that they are highly effective. And this is also shown in my Corona program in Python. So for the computations of the under-detection factor, and also for estimating the true number of infected, I wrote a few Python programs, and put them on our GitHub repository that you can see here, and put them in this folder, and they can be run in the browser. So they use Google Colab as a backend to let it run, and you can actually rerun these programs to obtain the newest data up to the last day. So that's very practical for rechecking what's going on recently. So you can simply click on this link here. So I click on it, and then we get to this GitHub repository of ours, and you can see it. Here I have two programs. This is the Python notebook, which runs in the web browser, and this is the pure Python file, which you need to download and run locally. So for simplicity, I made a link right into Google Colab, which lets this IPython notebook run in your browser. So here I have a few explanations. Maybe I can make this a little larger here. So here I have a few explanations for it, which you can read. And here's also a link to the previous video where there are some explanations. And here's also the corresponding websites where you see more links to videos and the references. So let's click on this Google Colab link, and it opens those programs. Yeah, so here you are. Can make it a little larger here. So again, now you have somewhat more detailed explanation. Here you can see my database, and this uses the data from the Johns Hopkins University GitHub server. So they download all their data to a GitHub repository, so very practical, which allows my program to read it in so that always the newest data is available. And these programs which then follow can be run by using runtime run all. So here you have runtime, and here you have run all. So let me just do it. Then you just have to click run anyway. And then you can see here in this symbol that it's running. Now it's running this first code block. And in this first code block, it reads in the data from countries which you can specify here in this line. So here are the countries, and you can see that you have a list of countries. Actually go on here, and the good thing is you can change it. So because this is run in the browser, you can also change it here in the browser and just enter different countries, for instance. But you also have to look up the population of each country and enter it in the corresponding order. So for instance, for France, if you don't know the population, you would open Google and say population France, and then it gives you the population of 67 million. So that's easy enough. So that's why I have the 67 here. Yeah, so this lets you do your own experiments. It also lets you make the list smaller, so you can remove a few countries. That makes the coming plots a little more easy to read. Then there's also a start date from which the plots are plotted. So here it's March 1st, 2020. So this is just before the corona pandemic started in Europe and the US. So this shows it from the beginning, but this is also something you could change. Right, so here now it reads in the corresponding data. So here first you have the corona cases. So this shows the total number of cases for each country up to that date. Here you have the corona recovered up to that date. And here you have the corona death up to that date. So remember, we need all three for the underdetection rate. Right, so here it just reads then the data from the desired countries. So here I'm using readout from the countries which are just specified here. Then I do a little bit conversion. Here I'm converting into a NumPy array so that it's easier to compute. And here I'm doing the plotting. Right, here I'm using matplotlib for plotting the data. So first I'm computing the concurrently sick. And the concurrently sick are the ones which are infected minus the ones which are recovered. Right, so where do we have it? Here you go. So here, concurrently sick is country cases. So the total number of cases of infections, detected positive cases, minus recovered, minus the dead. Right. So these are the ones which are not yet recovered and not yet dead. Right. So they are currently sick. So this is what you then get. So here's the date on the x-axis. So you can see here it goes up to, this should be October 9th, I guess. And here you can see this upper curve here is the US. Right? And you can see here the US has by far the highest number of concurrently sick or actively sick. And when we look at Germany, Germany basically disappears down here. So Germany has a very low rate. But then again, it's also difficult to compare because these countries are very different in size. So the US has over 300 million people and Germany has somewhat over 80 million. Right? So it's about a factor of 4 between the two. Similar here, India has about 1.3 billion. So it's hard to compare because those countries have very different sizes. So that's why it makes to divide by the number of inhabitants in millions. So here I have the concurrently sick per million inhabitants. So that's why I needed this line with the inhabitants in millions, because then I can divide by it. Basically normalize to the population. And this is then the corresponding plot that we get. So here the same dates. And now we see the US here is still very high, but it's not dominating everything as in the previous plot. And actually here, the green one, which is Spain, just surpassed the US. So that shows that Spain is actually in a pretty bad position here because it has so many concurrently sick per million. Germany also becomes visible now here. You can see here in March it had a peak at around 1,000 concurrently sick. Then it went down during the summertime and now it's going up again here. So you can see a clear uptick here in the last few days. But it's still relatively low compared to the other countries. Right, so here, for instance, this is Lebanon. Lebanon also has a problem. But worse is this one here, which is France. So here, this is France. France has a similar trend as Spain, just a few days behind. So that's also troublesome because it seems here it's getting out of control. Yeah, so this actually gives you a good indication of where each country stands and what's the development over time, in which direction is each country heading. So we see here in the last few days, basically most countries have a clear uptick. And that's probably because fall is coming. Yeah, and then using this plot, you can also see the effect of social distancing and mask wearing, which was introduced in March. Right, and that's why I showed an enlargement for March and April in this plot. So basically it's the same plot, concurrently sick per million inhabitants internationally, but now just March and April. So here you can see it goes up to beginning of May. And here the orange curve is again Germany. Right here, Germany. And you can see here in end of March, there was the start of Germany's corona restrictions. And you can see here about a week later, actually the curve, instead of continuing to rise, like here the US did, we had a decline all of a sudden. So that's remarkable. Similar to Austria, right? They introduced those measures a little bit earlier, and that's why they also had an earlier decline here. Germany also here, clear decline. And even after those staying home orders were loosened and replaced by masks, it still goes down. So that shows that mask wearing is about as effective as staying home. So that's pretty good. And this actually gives hope, because mask wearing is so easy, right? It's cheap and easy, and it's easy to do. It's much easier than staying home. So that's why everybody should do it, because we have a easy tool against this pandemic, right? And of course, here in the US, mask wearing was becoming a political issue. Like one half of the country was agreeing to it, the other one was not. And as if in effect, that didn't work, right? For mask wearing, basically everybody has to wear it. Otherwise, it doesn't really work. And this is what we can see here for the US. It goes up and up. And it's basically quite stupid to make this a political statement, this mask wearing, which is basically a health measure, human health measure. So it should be a no-brainer to wear a mask. Yeah, now we come to the underdetection rate. So in this plot, I compute the underdetection rate, and I assume a 2% infection-based fatality rate. Right? But keep in mind that can vary a lot. So I say times or divided by a factor of 2 is the accuracy here. But still, it gives us a good indication. And also, most of all, a good comparison between different countries and a development over time. So here we can see it. So I computed the underdetection rate for each country that we just saw, and here's the resulting plot. And we can see in the beginning of the pandemic, here in March, the underdetection rate was very high. So testing was not very widespread, so the underdetection rate was very high. So, and then after the pandemic became more widespread, testing became better. For instance, here in Germany, you can see in the end of March, it dropped almost suddenly to a much lower rate. So Germany was very good in testing very early on. Then you can see here Brazil is the red one. They took a long time until they developed good testing, and then it also decayed only slowly, and recently, like since August, they are doing a good job. Even worse, the United States, here violet, they have in the beginning also they have a very high underdetection rate, factors of 40 and such. And then they become slower, but very slowly, lower, very slowly. So you can see instead of a sharp drop like in Germany, they just have a slow drop in the underdetection rate, which is still going on. So it looks like they are dragging their feet or having other issues here. And this is probably also, again, where politics come into play, right? Politics hinders here the development or the deployment of the tests. If there's one party saying, oh, we have no problems with corona, then why should they test, right? So now we can use this underdetection rate to estimate the true concurrently sick. If we have this factor, right, then we can multiply our number of detected with this underdetection rate, and then we obtain the true concurrently sick, right, independent of the test rate. So this allows us to compare different countries much more precisely, because this allows us to compare different countries even though they have this different amount of testing going on. So this is actually a very interesting plot, and that's also why I plotted it in such a way that you can now zoom in. You can see it. So here you can again see the different countries, and here you can see the evolution of the concurrent infected. So here you can see May, and when you look at roughly mid-May here, you can see the US. You can see it actually has a hover over function, this plot, so this is very practical too. You just move your pointer over the curve and then you can see the country and the value. So here you can see we have 44,000 concurrently sick in the US in May. So this was already a very high value, but at the time they didn't see it because there was only very little testing going on. So they had a very high value very early on. And you can see it stays more or less constant, right? So actually the increases of the values that we see from the US comes mostly from discovering the infected after a while. But they had a bad value very early on and just didn't see it because there was insufficient testing. So here basically it stays flat most of the time, and I find this actually one of the most surprising results of this plot, that the US has more or less a very high value of concurrently sick, and it's not changing that much. It's basically like a big body of water that is flowing through the country to the different corners. So the total number stays the same, but it's distributing in different places. Yeah, interestingly here, those curves here from France and from Spain surpass the true concurrently infected per million of the United States in September, in late September. So now, already in late September, they surpassed it. And now they are really high. So now they're at over 100,000 per million inhabitants. So it's like almost 10% of the population is concurrently sick. So that's a really dangerous situation where I would say it's hard to get under control because there's so many already infected. Now we can compare it with Germany. So there should be a zoom tool, which I cannot really see here. Where's my zoom tool? Yeah, so here I have my zoom tool, the zoom box. When I click on it, I can mark an area and enlarge it. And here you can see Germany is about 700 true concurrently sick per million inhabitants. So even though it went up recently, here this black curve, you can see it goes up, it's still orders of magnitude below other countries like Lebanon or Italy or France and Spain with 100,000. So that's a factor of over 100. So it's not that bad yet in Germany, but it can easily be. When you look at those countries around us, the viruses will not stay there, right? They will come. That's why it's important to obey the mask wearing and the other corona measures, because we really need them. Otherwise, we will get very high infection rates, and with it, very high death rates. So here we have the resulting death cases per million inhabitants. And we can also compare the different countries here. So interesting is that in the beginning of the pandemic, most countries had a strong increase in the number of deaths, which means a high number of deaths per month or per week. And you can see here Germany's curve flattened, which means that during the summertime, not that many people died from corona. Unlike, for instance, Brazil, here this red curve, goes constantly up, which means they have a high death rate all the time. Similar here for the US. So it's more or less constantly going up. And recently we also have here the green curve, Spain, going up. So they also now have again a very high death rate from the high infection rate that they have. Also here France is going up. And similar here down here, Lebanon. Here we have India. Germany is still flat, but that's more like an outlier internationally. So most countries actually see higher death rate, and it can be expected that Germany will have a similarly increased death rate when we have increased infection rates in fall. So that shows why it's important to follow those corona measures like mask wearing and social distancing and such, to avoid this increase in death rate. Yeah, also you can see that the overall number of deaths per million is very different. So here in Germany we are still at the lower end compared to countries like the US or Spain or Brazil, which have on the order of 600, 700 deaths per million. Although this is the accumulated death. So this is the number of deaths from the beginning of the pandemic, right? The sum of the death. So here we have about somewhat over 100 in Germany. So that's about a factor of 6 to the US or Spain or Italy. And so we are still doing a good job, and we should make sure that it stays this way. Yeah, and to predict how it can continue with the current state, we can compute an increase factor of the concurrently sick, which I did here. So basically, I plot here the increase factor, the day-to-day increase factor of the currently sick. And here you can see the last few days up to October 9th, it's already quite high compared to previous days. So it generally fluctuates somewhat, and it's often that you have a weekly fluctuation here because during the weekends often the numbers are not transmitted. So that's why it's good to have a 7-day average, and that's also what I do for my prediction. I compute a 7-day average of those increase factors, and then I assume that this 7-day average stays constant over the duration of the prediction, right? And this is also a somewhat realistic assumption, and in any case it shows how it will continue if we don't change anything. So in the current state, how it will continue. So this shows also if we need to have a correction or if everything can stay as it is. So this is actually a good indication of how good we are or not. So currently it's not so good. So here's my prediction then. And here we can see I'm doing the averaging over 7 days here. I can actually change it here in the browser by entering a different number. You can also try it with different numbers and see how the result changes. And let's try 31 days, a month, and then I can let it run with those new numbers. So here this button lets you run this code cell, and then it plots the result down here. And you can see it's doing a prediction from the beginning of October to the beginning of November. And you can see here Germany is slowly increasing. So here we have 5,000 concurrently sick, and this is I guess over 1,000, maybe 2,000. So this is already quite an increase from coming down here maybe 300 to almost 2,000. So It's still relatively low, but it's going up. So especially low when you look at the comparison here. France, right? France is crossing the United States here in end of October. Spain already surpassed the United States in the number of concurrently sick. And Lebanon here increasing a lot. We are still relatively low. So now we can actually try to see what happens when we extend it to 3 months, 91 days. So let it rerun. And now we can see, now it's not so good anymore. So now we are coming into the middle range. So we actually surpassed Brazil here, right? So Brazil is surpassed somewhere in early December here. So that shows that the current numbers are not so good, right? If we don't change anything with the current numbers, we will get into problems. Here, this is the United States, right? So you can see here that Spain, France, Lebanon, they all surpass the US a lot. And even we come close to the US if we continue like now. So that means we really need to be careful. Don't get into touch with too many other people on big parties without masks, but instead wear masks, particularly when there are many people around, and keep social distancing. And just do common sense measures, corona measures, right? So that's important to avoid this strong uptick here in the beginning of the next year. And this also shows you that this time period, the beginning of next year, is probably more critical than, say, now October or November. So I guess October and November will still be relatively fine, but then once we come into December or January, that's the dangerous part, because that's basically also traditionally where the flu season hits hardest, right, in the winter months. So this is still coming up. So I just can recommend staying safe. Okay. Yeah, so this is what we just saw. So basically, when you look at numbers at early September, Germany had about just 220 concurrently sick per million, so relatively low number. But at the same time, the US had already 11,000 concurrently sick. So that's a factor of 50 times as many as in Germany. So if it doesn't go right, it really can go wrong. Germany has about 110 corona deaths per million inhabitants so far, right? So far we are quite good. But the US, Brazil, Italy and Spain all have over 600 deaths per million inhabitants, which is a factor of 6 or more over the course of the pandemic up to now. Yeah, so also observe again that you can change the countries in the program together with its population in million inhabitants. So this is for you to do your own experiments to see what changes when you change different things. And I found that actually quite helpful to see what happens and to basically understand the connections between the different variables. Okay, so yeah, have fun doing that, and then see you next time. Bye bye.